fabulous chemistry students.
Hey everybody.
That's MoNaCo.
And that was Milks,
We are starting Unit 12.
the last one of the year.
Oh, say it isn't so.
Hey Mister, when are we gonna be done? In about six videos, maybe 7.
That's it.
That's
No,
it.
yeah,
You are done,
6.
and then you got a review for ours and the state final.
Yes, we do. So, on to Unit 12. What do we need to know? Our unit objectives.
Always, we want to let you know what your learning targets are. So here
Right.
they are.
And there's a lot of them, guys, for 6 videos. Might think it's going to be a walk in the park. There's a lot of information.
Yeah, so we're going to predict stability of an isotope based upon ratio of neutrons to protons to the nucleus. I'm not really going to throw you questions like this, but I am going to show you the reference table that shows all the radioactive isotopes, and so you're going to have to know that that's where I go.
Right.
Table N.
Right. And then we learned about, 83 protons. Anything over that is not
Stable. It's naturally radioactive.
And we're going to understand that while most nuclei are stable, some are unstable and spontaneously, all by themselves, decay. And it happened to emit radiation.
Yep, and this is happening all the time. So we're going to also calculate the initial amount of the fraction remaining, or the half-life of the radioisotope, using the half-life. We're not going to show you an equation per se. We're going to show you a chart. And this should be, hey, remember Earth science. You did some half-life back then, where we really talked to your Earth science teachers to try and figure out how we could make it the same.
Yeah, we'll do a lab with some M&Ms or something.
For sure. Should be very familiar.
We do need to understand this whole concept of half-life, being that half of the stuff is left.
Not radioactive. Half of it decays.
Right.
The other half doesn't.
Right.
Okay. There's 3 types of radioactive emissions, and you have to know the mass, charge, and power of them. Okay?
Right, and good thing about our reference tables, they're there.
Yeah, the mass and the charge are, but the power, the penetrating power, is the fact that you got to remember.
Yeah.
So let's see them.
All right, well, let's do them. So alpha, beta, positron, and the big bad daddy, gamma.
Gamma, yeah. We're going to deal with the alpha, beta, and gamma radiation penetrating power-wise. Positrons isn't really part of the literature, but they penetrate just about as much as a beta particle does.
Yeah,
So,
because they kind of are. Determine the type of decay. Is it alpha, beta, or positron, or gamma, and write the nuclear equations. Again, there's a reference table to help us with this.
reference table N, it tells you what the radioisotope is, its decay mode,
And
half-life,
how many
as
years
well
or
as 2
days
different
or
ways
seconds.
to write the notation. So,
Right. Then we got to figure out what's the difference between fission and fusion. These are our 2 nuclear reactions, if you will. One's going to be cutting in half, and one's going to be slamming together to make a bigger molecule. One happens in the sun. We can't do it here.
One's like a synthesis, and one's like a decomposition.
Yeah. We do fission here. Humans can do fission here on the planet. I think we can kind of do fusion, but not readily and not.
We have not created a sustainable chain reaction of a fusion.
There. Are you feeling smarter yet, Professor? Go.
We want you to be able to tell the difference between a natural and an artificial transformation or a transmutation. So how do you know that this equation I show you is natural or is it artificial? It's very simple, and you'll see in the vocabulary as well as the lessons.
Yep. Be able to complete nuclear equations, predicting the missing particles from the nuclear equations. Basically, this is just conservation of mass.
Yeah.
You know, you got a mass on one side of 222, decomposes into X plus something with 220. Well, 220 plus what equals 222? You figure it out pretty quick.
This is some algebra, brah.
Yeah, barely.
Barely algebra. Barely. Understand the change in energy in a nuclear reaction. So in the labs, as well as some of the activities here, I'm going to invoke my hero, Albert Einstein, and his most famous equation ever, E equals mc squared, relates the relationship between mass, energy, and the constant, the speed of light. So how come a nuclear weapon explodes and makes such crazy energy? Or how come a nuclear fusion reaction squeezes 2 nuclei together and makes so much energy? It all relates to Albert Einstein.
Yeah. MoNaCo's going to get his geek on for sure. Be aware of the risks associated with radioactivity. We're going to compare and contrast some good and bad with nuclear power, so to speak.
For sure. And beneficial uses and real-world applications of some radioactive isotopes, specifically for medicine and power.
Yep. Carbon dating.
Yep.
That kind of stuff. So, So here they are. Here's some radioactive dating, tracing chemical and biological processes. That's good. There's that good video we saw where like somebody's kidney was blocked and they found it because all of a sudden, look,
Yeah.
tracer stopped there and didn't move.
A lot of these things, maybe even you've had some of them done on you.
Sure.
Nuclear power, you're burning it right now. Detection and treatment of diseases. So a lot of good applications for nuclear power, radioactive isotopes.
Yeah, I think it goes kind of under the radar that we have a nuclear power plant 20 miles from here, right up on Lake Ontario.
If that one went into meltdown and had an issue,
we would be in trouble.
All of Rochester would get evacuated, and if it went into meltdown, like one of the movies I'd like you to watch in this unit, we probably wouldn't ever be able to come back and live here.
Just like they're not allowed to go to Chernobyl now. You see a lot of those
30
movies
years
now.
later, you still can't go to some of these disasters.
It's going to be a few thousand years, probably.
Yeah, more.
And guess what? Oh, new part.
New part.
Ooh.
We want you to keep track of your assignments. We've been kind of doing it for you all along with our trackers and whatnot. So let's see what you got here.
So, of course, you have this unit packet that you're holding in your hand right now.
Mm-hmm. Castle quiz.
Pretty rudimentary.
Pretty rudimentary. You would do a self-castle. For me, that's going to help your castle quiz grade.
Right.
Yep.
Yep. So definitely got to create one yourself. We're going to have your normal vocab quiz.
Just like always.
That next video you'll be ready for as soon as you're ready. There is one Half-Life lab. Good choice. Or good news. You get the choice between M&Ms or Skittles.
And also good news, you probably did one very similar to this in Earth Science.
Right. We're going to make you make some graphs and you'll have fun.
Pogo on fission and fusion.
Got to be able to differentiate the two things.
Yep.
Another Pogo on the nuclear reactions themselves.
Conservation of mass and nuclear changes.
Beautiful.
And then we got an exam.
Big bad test.
The faster you finish this unit's assignments, the quicker you can start reviewing for the final examination and stepping up to the plate, showing everybody around you that you have what it takes.
And just a little hint right now in case you're not bumping. That's where your grade gets to skyrocket fourth quarter in chemistry with Milks and MoNaCo.
You might go into review time with a very low grade.
There is something like, 8 boxes here? So as you go, I want you checking these things off as you complete your assignments, please. And then when you're done, before you turn them in another box, why don't you tell us how you think you did on the unit completing all these assignments?
Mm-hmm.
Was it about 80%? Were you 90%? Like, how are you feeling about how you did?
Yep.
And then maybe we'll take that into account when we grade it.
Yeah.
You know what I mean?
So there you go. Keep an eye out for each of those topics as we go through them. Check them off as you complete them. And, just know what's coming up.